Pipe jacking and microtunneling are becoming increasingly important for the installation of new pipelines, as well as the renovation of existing pipelines. The Herrenknecht AVND series, introduced in this film, has been deployed throughout the world with great success. The ability to change from slurry to mixed shield mode during continuous operation means that it's possible to tunnel in a wide range of geological conditions and non-homogeneous materials. In the computer simulation that follows, you will see the technical requirements from the planning phase through to completion of the pipeline. A pipeline with a diameter of 2 meters will be driven from the launch shaft to a target shaft 500 meters away. The advantages of the pipe jacking and microtunneling process, in contrast to conventional methods in a construction project of this nature, are as follows. Drastically reduction in the movement of excavated soil minimizes costs. It's an environmentally friendly method that causes minimum disturbance along the construction routes other than at the working shafts. Lowering of the groundwater level is avoided, thus preventing dangerous settlements of building foundations and road surfaces. There is virtually no disruption of the flow of traffic, apart from a slight disruption in the area of the job site. Traffic continues to flow without hindrance, highlighting the advantage of the conventional of pipe laying in urban city areas. Last but not least, construction work is not influenced by the weather, resulting in more rapid completion and deadlines being met. A further advantage of pipe jacking and microtunneling is the opportunity to drive a curved alignment. The vertical curve radius, in this case 1500 meters, allows the riverbed to be tunneled under from a shallow working shaft. The minimum cover from the crown of the tunnel should not, however, be less than twice the external diameter of the pipeline. In this case, the base of the start and target shafts are located only about 8 meters below ground level, whereas the deepest point to be tunneled is 38 meters below ground level. In order to determine the geological conditions, boreholes are normally made along the planned route. As an example, we will now examine the borehole at the point of the tunnel with the least cover. The particle size distribution diagram classifies the material groups clay, loam, sand and gravel according to the grain size. As the grain size increases, the permeability of the soil increases with a subsequent increase in the water inflow. The areas best suited to slurry systems, as used with the AVN 2000, are marked by the green area. Selected borehole material is passed through a series of sieves of varying sizes, the results being entered in this diagram called a grading curve. The evaluation of all boreholes along the route indicates the spectrum of grain size distribution that can be anticipated during tunneling. In this case, it lies within the area of operation designated as the suitable operating range. The construction site at the start shaft is secured with a coarse gravel and compacted to take the loads imposed by the crane, etc. Then the start shaft is constructed, in this case using the sheet piling method. It's also possible to construct the start and target shafts by other methods using, for example, precast concrete segments, in situ concrete shafts, etc. The start shaft must be adapted to the requirements and strengthened, if necessary, to be able to withstand the jacking forces. The product pipes are normally delivered by truck and stored at the site. Dependent upon the availability of space, a pipe stock is established and maintained as necessary. The tunneling machine is delivered to the site in separate modules for easy handling. The container with the operator control panel and the hydraulic power pack for the jacking station is located in front of the start shaft, such that the machine operator has eye contact with the jacking station. A separation plant is used to separate the excavated material transported from the tunnel phase by the slurry system. Bentonite suspension is used to support the working phase and to convey the excavated material to the surface. After separation, the bentonite suspension is then recalculated to the tunnel phase. A further bentonite pump is using to supply lubrication around the outside of the jacking pipes. The speed-controlled slurry feed pump conveys the regenerated bentonite suspension from the separation plant to the cutter head. A speed-controlled slurry discharge pump is installed in the return side of the circuit. In order to prevent cavitation, it's set up in the start shaft and also connected in the separation container. The hydraulically powered main jacking station is installed in the start shaft. The thrust ring ensures that there is an even transfer of force from the 4 hydraulic cylinders. A concrete block cast in the rear of the start shaft absorbs the forces created by the thrust cylinders. The cutter head and the first machine pipe are assembled and can now be lowered into the start shaft by the side crane. The jacking station can generate a thrust force of up to 1,400 tons on the pipeline slide rails, provide precise positioning of the machine sections and the subsequent jacking pipes. A launch seal is necessary in order to ensure a watertight seal around the pipe and prevent the leakage of slurry and bentonite lubrication into the shaft. Normally, a low-strength concrete block is cast against the sheet pile wall at the exit point. The launch seal assembly is installed at this point by bolting to the concrete block. Next, the cutter head and the first machine pipe, complete with the drive unit and steering cylinders, are lowered and positioned in front of the launch seal. The second machine pipe is lowered and connected to the first machine pipe. The feed and slurry discharge lines are connected. The tunneling machine now carefully cuts through the low-strength concrete block. After the last machine sections have been installed, the tunneling machine is complete and is now ready for the pipe jacking operation to commence. The cutter wheel and tools are adapted to the expected geological conditions. The crusher chamber is located directly behind the cutting wheel. During operation, the chamber is completely flooded with bentonite. The reinforced spokes of the wheel act as a grinding mechanism on the same principle as a coffee grinder. The larger rocks are reduced in size until they can pass through the opening of the screen for transport in the slurry circuit. The slurry discharge pipeline, shown in green, transports the excavated soil together with the bentonite suspension. During operation in hard rock or cohesive soil, the slurry circulation is leaded through the cutter head nozzles. In sandy soil, the slurry circulation is leaded through the annulus nozzles located behind the crusher cone in the excavation chamber. In mixed shield mode, the chamber behind the crusher cone is flooded with bentonite. In this mode, pressure compensation with the crusher chamber takes place via the communication pipe. The slurry and feed lines run through this chamber. The steering cylinders are situated in the first machine pipe and are used to adjust the direction of cutter head with millimeter precision, thus making it possible to correct the line and level. In addition, a laser target is located in this machine pipe for determining of the position of the machine. Power for the steering cylinders and cutting wheel drive are provided by the hydraulic power pack. The feed and slurry lines are equipped with the compensators to block vibration movements and to realize a length compensation. A compressed airlock is located behind the first machine pipe. When it's necessary to make repairs or replace tools, the maintenance personnel are able to gain access to the cutting wheel and excavated face under the safety of compressed air. Finally, a telescopic station is located at the rear of the machine. This provides constant thrust of the cutting wheel, particularly necessary in rock excavation, and ensures smooth advance of the machine. The slurry feed and discharge lines pass through the entire machine and along the tunnel to the separation plant. The material transport system is a closed system. The blue lines feed the bentonite suspension to the excavation chamber, and the green discharge line transports the bentonite suspension and excavated material to the separation plant, where it's separated via vibrating screens and hydrocyclones. In order to ensure that the tunneling is safe and controlled, the forces exerted and the working phase have to be kept balanced. The earth pressure, shown in brown, and the water pressure, shown in blue, are counterbalanced by the machine with the pressure of the bentonite suspension in the excavation chamber. The bentonite suspension permeates the soil ahead by means of a light overpressure. The machine is in a slurry mode with the cutting head nozzles in operation. When a coarse-grained gravel layer is reached, the machine can be changed to mixed shield mode, where it's possible to make finely controlled to slurry pressure with the aid of compressed air and better build up a cake of bentonite at the face. This improves the support of the working phase. The second chamber, which has been dry up to this point, is flooded for the changeover to mixed shield mode. Compensation for the pressure at the working phase is achieved via the communication pipe. The second chamber is subjected to air pressure. The pressure tends to fluctuate more heavily due to greater permeability of the coarse-grained size material and can be compensated via the compressed air cushion, which is used as a spring damper system. If there are high flow losses, more bentonite is pumped into the second chamber. Adaptation of the operating mode to the geological conditions means that it is possible to master a varied range of geological conditions. This technical advantage extends the range of operation for the AVN system. The position of the tunneling machine is monitored with the assistance of a laser-supported measurement system. For level routes and lengths of up to 300 meters, an electronic laser system, ELS, is deployed. In this case, the laser is located in the start shaft and the target in the machine. The point at which the laser beam meets the laser target is determined electronically and is transferred via a data cable to the evaluation computer in the control panel. There, the measurement data is shown on the monitor in graphical and numerical format. On longer tunneling routes of more than 300 meters or curve drives, the so-called Steuer Light System SLS-RV guidance system continuously provides the shield operator with updated information about the location and direction of the machine. On the basis of this design, it's possible to steer both horizontal and vertical curves. Following the startup phase, the component parts of the service system are installed in the forward area of the tunnel and move forward with the pipe jacking without eye contact to the launch shaft. In the pipeline, the servo motor-powered laser theodolite is adapted to an automated tripod. There's an active laser target in the MTBM, which acts as the receiving unit for the laser beam, as well as a simple prism for measuring routes. In the pipeline, there are 3 measurement prisms. 1 is used as the connection target and 2 as reference prisms for the automatic measurements of the tunnel alignment. In order to record any effects of roll of the tunneling machine or pipeline, these are equipped with single-axis inclinometers. Presentation of the spatial position of the machine is made by means of a white crosshair and a red crosshair, that is, position of the machine in cutter head level. The set value of the machine position is shown by means of a fixed crosshair. During tunneling, the friction forces around the outside of the jacking pipes have to be kept as low as possible. The normal method of doing this is to lubricate the annulus around the jacking pipes by injecting bentonite. Every 3rd to 5th jacking pipe is equipped with a bentonite lubrication station. These pipes each have 3 injection points that are connected to the bentonite lines. The solenoid-operated valve at each point enables controlled, metered injection. The bentonite is injected with light pressure into the annular gap between the pipe and the ground and spreads over the surface of the pipe. It permeates the surrounding soil, providing a considerable reduction in friction. A further measure aimed at keeping the jacking forces of the tunnel under construction at an acceptable level is the deployment of additional jacking station. The so-called intermediate jacking station consists of a steel shell with the hydraulic cylinders installed. For demonstration purposes, an intermediate jacking station located directly behind the main jacking station is used here to clarify the principle. In reality, an intermediate jacking station would be deployed at a distance of roughly 100 to 150 meters behind the tunneling machine. The jacking force of the main jacking station is then only effective of up to first intermediate jacking station. When the main jacks are extended, those in the intermediate jacking station are retracted. Afterwards, the main jack is locked in its position and then serves as a thrust block. The intermediate jacking station braces against the section of the pipeline behind it and pushes the part in front of it further forwards. Loadings along the pipeline are thus maintained at minimum levels. In this way, a number of intermediate jacking stations situated one behind the other make even long-distance tunneling possible. With the aid of bentonite lubrication and intermediate jacking stations, the whole route can be advanced without intermediate shafts. In the target shaft, the machine is disassembled and removed. After completion of pipe jacking, the manholes are finished and the new pipeline can go into operation. In this animation, some Herrenknecht innovation in the area for long-distance pipe jacking have been illustrated. These developments result in a reduction of the overall construction time required for long-distance tunneling in order to make construction more cost-efficient and to avoid possible complications.